Okay, so let's take a look at the dreaded sprinkler problem from exam 2. So this was probably the single hardest problem on the exam. I think one person got it completely correct, one person was very close, and everyone else lost at least a substantial amount of credit on this problem. So it was fairly difficult and required a combination of lots of different concepts that we've discussed. And putting all those things together required a lot of careful mathematics. So let's take a look at how you do it. So the first part is not so bad, actually, and I think most people got this mostly right. We have to verify that h of t equals negative 5t squared plus 3 sine of theta t is a solution to the given differential equation. And so the first thing we notice is that h of 0, if we plug in t equals 0, these two terms are both 0, so it satisfies the first initial condition. Let's calculate h prime. One thing a lot of people messed up here is that in this problem, theta is just a fixed angle, right? The water is getting shot, and then after it gets shot at a given angle, it just follows this trajectory, which depends on that angle. So when we differentiate, theta is a constant with respect to t after the water has been launched. So therefore, we only get negative 10t plus 3 sine of theta. And we can check that h prime of 0 is equal to 3 sine theta, because when we plug in t equals 0, this first term goes away and we're just left over with this. So it satisfies the second initial condition. The only thing left to check is to make sure that h double prime is equal to negative 10, and we can see that that is indeed the case from this formula. Okay, so part B was where the difficulties really start to appear. So we first have to figure out what's going on here. So we have this parabola, which is h of t equals negative 5t squared plus 3 sine of theta t. And this is the trajectory that the water is going to travel. So here's the ground. Here's the sprinkler, which I'll label like so. And so we shoot it out at an angle, and it follows the trajectory of h of t. And at some point, it's going to hit its maximum value m, which will depend on the value of theta. So if theta is higher, maybe it shoots a bit higher. If theta is lower, it might shoot a bit lower, and so on. So we'd like to find what is the value of m for a given theta. Well, m is where this function has its maximum. How do we find a maximum? We take the derivative and set equal to 0. So h prime of t is equal to negative 10t plus 3 sine of theta. We want to set this equal to 0. If we rearrange this, this implies that t is equal to 3 sine of theta divided by 10. So m is going to be the height of the water at this time. So m is equal to negative 5 times this value squared plus 3 sine theta times this value. And so we can simplify this a bit. When you square this, you get 9 sine squared of theta divided by 100. Multiply by the negative 5, and you get negative 45 sine squared theta divided by 100 plus 9 sine squared theta divided by 10. Find a common denominator. and you'll get 45 sine squared theta divided by 100, which is the same as 9 sine squared of theta, all divided by 20. So this is the value of m, which depends on theta. But now, as theta varies, m will vary as well. So let's take the derivative of m. So if we take the derivative of m with respect to t, because theta also depends on t, we have to use the chain rule. So we'll get 18 sine of theta times cosine of theta. Then also we have the derivative of theta itself. So we have two chain rules here. One chain rule just to take the derivative of sine squared, and then one chain rule because theta itself is also a function of t. We still divide by 20, but now we can plug in things that we know. So theta, we're interested in the moment when theta is pi over 4. When theta is pi over 4, sine and cosine are both square root 2 over 2. And we're told that theta prime is equal to 1/10 divided by 20. This all simplifies to 9 divided by 200, and our units are meters per second. So that was the solution to this problem.